Good afternoon, learners. I welcome you back in the second session that we are going to start. This session basically pertains to sampling and sampling distributions, and as I said that this is the basis of all the analysis that we do in testing of hypothesis and estimation. So it is one of the very important topics of the inductive statistics, and since it gives you the fundamentals behind testing of hypothesis and other distributions based analysis, this is a very important topic. So without wasting time, I would like to go on the lecture part of it, and we'll see in the second slide that basically once you collect a particular sample, what are the things that you do with that particular sample? That you estimate the values of a population parameter, you test a statistical hypothesis about the population, you compare two or more populations, and you perform correlation and regression analysis. Now, these are the four things that you do after you collect a sample. So first point is that you estimate the value of a population parameter on the basis of a sample parameter. And what is meant by this? Suppose you want to find the employee satisfaction of all the nationalized banks in India. Now, your time frame is very less, and you could not finish interviewing all the employees of all the nationalized bank in India. So what you will do is that you will collect a small sample that is representative of this population, and from the sample, once you calculate the sample mean, you would say that this mean is the estimate of the population mean. That means it is the estimate of the satisfaction level of all the employees over the country. So one function that you would like to do after you collect a sample is that you want to estimate a population parameter. The second one is that you set up a hypothesis about a population parameter, and you apply testing of hypothesis in order to derive inference about a particular hypothesis from the sample, and then you would like to generalize that statement for the population. So testing of hypothesis is the second activity here. The third activity is that you want to compare two population parameters. And how do you compare? Say you must have seen the t-test of comparing the mean of two populations, in which basically the mean of a particular trait in two populations is being tested with the help of t-test. So this is the third activity, that you would like to compare two populations. And the fourth one is that you want to find the correlation and regression equations, and you want to test various parameters of the regression equation, and you want to test the correlation. So basically the three activities are pertaining to testing, and one activity is pertaining to the estimation once you have a particular sample or a statistical data in your hands. Now, what is sampling distribution? Let us define the word sampling distribution. Sample statistics is a function of n sample values, x1, x2 up to xn. Sample statistics is a random variable and therefore has a probability distribution or a probability density function. It is also known as the sampling distribution of the statistics. So you are having, suppose you are having n variables in the sample. These n variables are denoted by x1, x2, x3 up to xn, and the distribution attached with these sample values is called the sampling distribution of that particular statistic. Now the question arises why we want to study the sampling distribution. Sample statistics form the basis of all inferences drawn from populations. Probability distribution of sample statistics allow us to calculate the probability that the sample statistic assume a particular value. Important and very important point to understand, this ability to calculate the probability that sample statistics lie in a particular interval is the most important factor in all statistical inferences. Now, what is meant by the statement that I have just made? That will highlight the importance of sampling distribution. In sampling distribution, what you are doing is that you are assigning a frequency with all the sample values, and basically on the basis of this frequency you are calculating the probability. Now if I am talking about a particular sampling statistic, that is sample statistic, that is say mean of the sample, if I am able to assign probabilities that the value of mean would lie in a particular interval, then I am 99% done, in the sense I have assigned a probability value that whatever is the population, this value is going to lie in this particular range. So that solves many of my purposes, and this is the most important thing that one needs to understand when one talks about the statistical inference part. And this is why the study of sampling distribution is of prime importance. Now you can see the slide which defines the sample mean. So we have named it as sampling distribution of mean, and we have already denoted the sample by the values x1, x2, xn. So sample mean is defined as x bar, which is x1 plus x2 plus up to xn divided by n. Now for another sample of size n from the same population, we might get a totally different set of values and so a different sample mean. There are many, perhaps infinite possible values of the sample mean. What is meant by this statement, that there are infinite number of values possible for the sample mean? Now suppose you take a population of say 100 and you want to choose a sample of 5 from that population. Can you tell me that how many samples would be possible? The answer is there would be 100 C5 combinations of sample that you can make if you want to choose a sample of size 5 from a population of size 100, and this number is very big. So for each different sample you would be having a different sample mean, and unless you assign some kind of probability to these values do not have any meaning. So basically this is the sampling distribution of mean, and since there are infinite number of values, each time you change your sample mean is changing, so there are infinite number of samples. Now you could have two kinds of population. One is the infinite population and other is the finite population. So if your population is infinitely large, we will say this is infinite population, with the population mean denoted by mu and population variance denoted by sigma square. So if you are doing sampling without replacement, you would write expectation of sample mean x bar equal to the population mean, and variance of x bar is given by sigma square by n, where population variance is sigma square. The standard deviation of the sample mean is also called the standard error of the mean, and it is denoted by S square. So the standard error of the mean indicates the extent to which the observed value of sample mean can be away from the true value. I'll repeat it, that the standard error basically is an estimate that indicates how much your observed value of the sample is deviating from the true value, and why this is happening, that because of the sampling error this is happening. So you define the standard error of mean as sigma x bar, and it is denoted, it is given by sigma divided by under root n. Basically, standard error is of prime importance in testing of hypothesis, because if you closely observe the test statistic, normally the numerator of that particular test statistics is found from the null hypothesis that you set. So suppose you are comparing two population means, then your numerator would be x1 bar minus x2 bar. Alright, so halfway you are through. Now you talk about the denominator, and in the denominator you would always be having standard error of the thing that you have put in the numerator. So here it will be the standard error of x1 bar minus x2 bar, and once you are able to find the standard error of x1 bar minus x2 bar, you are ready with the statistics that you are testing. So just now we have described how the standard error of the mean is calculated, and we have said that this is denoted by sigma x bar, and it is given by the formula sigma divided by under root n. Now sampling from the infinite population, you have to make some kind of adjustment when you are talking about the finite population, and that particular correction is called the finite population multiplier. We'll be discussing about that. But if your population is infinitely large and you make an assumption that the random variables are involved are independent of each other, then expected value of sample mean is mu, and variance x bar is sigma square by n, which is given by sigma divided by root n. Now this is for the infinite population. If we talk of the finite population, and as I said that you have to introduce a term called finite population multiplier, and let us see what is this. If you see the first box on the slide, this is basically sigma square by n is multiplied by a term which is capital N minus n divided by capital N minus 1, and this term is basically called the finite population multiplier. So this is the only difference you have in a finite population and an infinite population. Population mean and population variance are given in the same manner as it was given in the infinite population, and sampling is done without replacement. Without replacement means if you take a object in the samples, next time you are not going to take that particular object. So it is without replacement. That means object once taken in the sample cannot come in the sample again. So the multiplication of finite population multiplier is the only difference in infinite population and the finite population, and the standard error is again under root of the variance, and it is given by sigma divided by under root n into the under root of finite population multiplier, that is under root capital N minus n divided by capital N minus 1. Now if you make your population very very large, that means if n tends to infinity, what will happen to the finite population multiplier? You just try to put infinity in place of capital N. So this expression would become in the form infinity divided by infinity, which will be unity, which is 1. So this term vanishes in an infinite population only because if n tends to infinity, then this finite population multiplier vanishes from the equation. That is the justification of what I was telling you. Now let us take a example of sampling from a normal population. A normal population, you all know that it is the basis of all the statistical inference that we do. So if x is a random variable which is following a normal mu and sigma square, that means a normal distribution with the mean mu and variance sigma square, then it follows that x bar has a normal distribution with mu and sigma square divided by n, and the normal distribution is a continuous distribution, so the population cannot be small and finite if it is distributed normally. So we are not using the finite population multiplier here. Now what is the new thing that I have told you here? There is nothing new that I have told you. In fact, we have calculated the expected value of the sample mean and we have calculated the variance of the sample mean. So we are just saying that if your random variable or if your sample, one variable in the sample is following a normal distribution with mean mu and sigma square, then x bar will also follow the normal distribution with mean mu, because expected value of x bar is equal to mu, and with variance sigma square by n, because we have just shown that variance of x bar in both the cases of finite population and infinite population is sigma square divided by n into the finite population multiplier. But if your population is big enough to be called infinite, then there is no need for the finite population multiplier. And this is what we have shown in this slide, that the normal distribution is a continuous distribution and the population cannot be small and finite if it is distributed normally, because there would be infinitely many values. Now let us take an example of sampling distribution. I'll read the question for you, that suppose the diameter of a component produced on a semi-automatic machine is known to be distributed normally with a mean of 10 millimeter and a standard deviation of 0.1 millimeter. If we pick up a random sample of size 5, what is the probability that the sample mean will be between 9.95 and 10.05? So basically what is given in the question, the given thing is that x is a normal variable with mean 10 and standard deviation of 0.01. In fact, the other thing is that your sample mean will have a normal distribution with 10 and 0.01 divided by 5. And why we are using 0.01? Because standard deviation is 0.1, so if you square 0.1, 0.01 would come, and this is the equation we have. So what is asked here, they have asked you about the probability that your sample value or sample mean would lie in the interval 9.95 and 10.05. So now you write it mathematically. And how do you write it? It is the first expression in the box which is shown in the slide, the lower box. What is happening here is that they are trying to find the probability of X bar lying between 9.95 and 10.05. So what they are doing here is that they have written probability 9.95 less than equal to X bar less than equal to 10.05, and what they have done is this, that they have tried to transform this in the form of a standard normal variate. And what do you do when you want to transform a variable into a standard normal variate? That you subtract from that variable the mean of the population and you divide it by the standard error. And this is precisely done in the second expression here, that it is done as probability 9.95 minus 10 divided by the standard error, that is 0.1 divided by under root 5. It has become a standard normal variate. And what is the expression that will be replaced by Z, which is the standard normal variate? It is X bar minus mu divided by sigma under root divided by under root n. Now this is equal to Z. So your equation has been reduced to a equation in terms of Z, and this has become probability minus 1.12 is less than Z is less than equal to 1.12 is equal to twice the probability 0 is less than Z is less than 1.2, and from the tables this value comes out to be 0.3686 multiplied by 2, so it becomes 0.7372. Now I would like to emphasize on 2 points here. Why I have multiplied the expression of probability by 2 here in the last step? Because my normal distribution is a symmetric distribution. So if I am interested in calculating the probability from minus 1.12 to plus 1.12, I can get it done into 2 parts. That means minus 1.12 to 0 and 0 to 1.12. Now since it is a symmetric curve, there is basically no need of calculating both these probabilities. It is a symmetric curve, so area under the curve on both the sides would be equal. That is why we have multiplied it by 2. And you are always provided statistical tables. They are given in your study material also. So what you do is that you refer to the normal distribution table, the standard normal distribution table, and from 0 to 1.12 you find out the area between the curve, which is coming out to be 0.3686. So your final probability that your sample mean would lie between 9.95 and 10.05 would be 0.7372. So this was the example that I wanted to give you, and this must have explained these concepts in a much better manner. Now I can represent this example in the form of a figure also, and now you can visualize what I was telling you. You can see that 9.95 to 10 is one area, and from 10 to 10.05 is another area. So the required probability that has been asked in this question is the shaded portion, shaded by slanted lines. So basically what is happening here is that I am calculating probability from 10 to 10.05, which I have transformed in the form of a Z variable, and I have calculated the probability from 0 to 1.12, which in other terms is meaning that I have calculated the probability from 10 to 10.05, and I have doubled that probability. I have multiplied that probability by 2, So I'm getting the end result. So this figure basically has given you enough explanation as to what we are trying to do and how the sampling distribution has helped us in achieving this. Another concept which is of prime importance in sampling distribution and statistical inference is the central limit theorem, and it is by far the most used theorem in statistical inference. And what it says that if x1, x2, xn are random variables which are independent and having the same distribution with mean mu and standard deviation sigma, then if n tends to infinity, the limiting distribution of the standardized mean will be z is equal to x bar minus mu divided by sigma under root n, and this will be a standard normal distribution. So basically, what is the central limit theorem? It says that for any variable, if you subtract from that variable the expected value of the statistic and you divide that by the standard error of that particular statistic, then you will be having a variable that will be a standard normal variate, which will be having a mean of 0 and variance of 1. So this is a wonderful result, and it had got many applications in statistical inference, especially in the testing of hypothesis, and we'll have some more example to discuss this particular kind of thing. Now, another important point here is that if your sample size is around 30, that means it is 30 or more than 30, then you can safely assume the normal distribution assumption. You can say that it is expected that my population has come from a normal population, and this is the assumption that is prevalent when you do statistical inference and you use sampling distribution. Now let us have some definitions, and we define the sampling distribution of variance. So till now we have defined that x bar, that means the sample mean, has a normal distribution with mean mu and variance sigma square by n. Now I want to find the sampling distribution of the sample variance, and sample variance I am denoting by s square, which is 1 upon n minus 1 summation xi minus x bar whole square. Now I want to find the expected value of s square and the variance of s square, and this I can find by expected value of s square is given by sigma square, and variance of s square is given by 2 sigma raised to the power 4 divided by n minus 1. So these two expressions are giving you the expected value of s square and the variance of s square. Let us move further and define what is a chi-square distribution. Now I am showing you a graph. In fact, all these curves pertain to the chi-square distribution, and it is very peculiar thing that chi-square is one distribution that changes its shapes on the basis of parameter that is called the degrees of freedom. That means the number of independent constraints. So if you have a 1 degree of freedom, then your chi-square curve would look like a bowl, slanted bowl. If it has 10 degrees of freedom, it will be much like a normal distribution, that means a symmetrical curve, or an inverted bowl. And if it is having 5 degrees of freedom, then it is a biased curve, and it has a longer tail on the right side. So these three curves explain that chi-square is one distribution that changes its shapes on the basis of degrees of freedom. So basically, let us define what is a chi-square distribution. The chi-square distribution has only one parameter, and this is called the degrees of freedom. There are many chi-square distributions with its own degrees of freedom. So that we have seen that on the basis of degrees of freedom, it changes its shape. In statistical tables, chi-square values for different areas under the right tail and the left tail of various chi-square distributions are tabulated. So basically, chi-square has only one parameter, that is the degree of freedom, and you can find the value of chi-square statistics from the table on the basis of degree of freedom. But what is a chi-square distribution? Let us define this. Let us go into the definition of chi-square distribution, because we all know that the ratio of two variances is F distribution. We'll come to that later, but for the time being, let us define the chi-square distribution. If x1, x2, xn are independent random variables, each having a standard normal distribution, then x1 plus x2 up to xn will have a chi-square distribution with n degrees of freedom. If y1 and y2 are independent random variables having chi-square distribution with y1 and y2 degrees of freedom, then y1 plus y2 will have a chi-square distribution with y1 plus y2 degrees of freedom. So basically, it is the sum of standard normal variates that is making a chi-square distribution. This thing should be very clear. It is the sum of standard normal variates that is making up a chi-square distribution. And the interesting thing is that the newer distribution would be having degrees of freedom, which can again be found out with the help of adding up all the degrees of freedom of all the variables that are added together. I'll read this slide for you, that if x1, x2, xn are random variables from a normal population with mean mu and variance sigma square, then xi minus mu upon sigma is a normal 0, 1. This we all have discussed. So xi minus mu upon sigma whole square, that means the square of a standard normal variate, is a chi-square distribution with 1 degree of freedom. So summation xi minus mu upon sigma whole square would be having a chi-square distribution with n degrees of freedom, and we can also say that n minus 1 s square upon sigma square, that means the ratio of sample variance divided by the population variance into n minus 1, is also having a chi-square distribution with n minus 1 degrees of freedom. So basically, I have given you 3 situations where chi-square variable is prevalent. Now let us go on to another important statistic, and you must have read the t-test, and let us see what is in the genesis of t-test. In actual practice, the value of population standard deviation sigma is often unknown, which makes it necessary to replace this with an estimate. And what was the estimate of sigma square? The estimate was s square. So in place of sigma, we are using s, which can be derived from the sample. So exact sampling distribution of x bar minus mu divided by s upon under root n is given by a t distribution. Alright, and why it is given by t, when earlier we were saying that it is defined by a z distribution? Because if your sample size is less than 30, then you will be using student t distribution, but if your sample size is more than 30, you would safely replace t by z, and you will say that this is a standard normal variate. So if x is a random variable having the standard normal distribution and y is a random variable having a chi-square distribution with new degrees of freedom, and if x and y are independent, then the random variable t is equal to x divided by under root y divided by nu. Again, I emphasize that x is a standard normal variate and it is divided by the under root of a chi-square variate. If this kind of equation is found, then we say that it is a t distribution, and it is also called the student t distribution with the new degrees of freedom. Student is the name of the inventor of this test, and his actual name was W.S. Gossett. So he was a mathematician but popularly known as student. Now this graphic is an excellent way of showing as to what is the difference between a t distribution and a z distribution. That means the standard normal distribution and the t distribution. You can see this, that the topmost curve is a standard normal distribution or t distribution with infinite degrees of freedom, and this is what I was emphasizing, that if your sample size is less than 30, you will name it as a t distribution, but if your sample size is more than 30, you would assume normality and you would go for z. So the first curve, there is no difference between the t distribution and the z distribution. Then you see the dotted curve, and dotted curve is t distribution with 10 degrees of freedom. That means it becomes a little flatter when you go to 10 degrees of freedom, and it further flattens if we take a t distribution with 5 degrees of freedom. So the peakedness of the curve goes off if we keep on decreasing the degrees of freedom. Now, as we were discussing about the relation between the t and z distribution, sampling distribution of x bar is known even when sigma is not known and when the sample size is not very large. If the sample size n is large, the t distribution with large degrees of freedom can be approximated by the z distribution. The t distribution is used when the degrees of freedom are not larger than 30. So if the degrees of freedom are larger than 30, the t distribution is approximated by the z distribution. Basically, this was all about sample mean. Now, there is another statistic which is called the sample proportion. And what is the difference between a sample mean and a sample proportion? In proportion, we divide that particular statistic with the total number of observations in the population, and this is why it is called the population proportion. So if you want to estimate a proportion denoted by capital P pertaining to a population, what you do is that you find a sample and you estimate the population proportion with the help of sample proportion, which is denoted by small p. So the assumption is that if n is sufficiently large, then p bar, that means proportion mean, would have a normal distribution with p and variance p1 minus p divided by n. So this is basically the result that we use in proportion. So it is having a mean of p and a variance of p1 minus p divided by n. This approximation works quite well if n is sufficiently large, so that both np and n1 minus p are at least as large as 5. Now, interval estimation we have already discussed, and I've told you that this is the best possible result that can aid in statistical inference, that if you can find an interval in which you expect your sample statistic to lie, and you can assign some kind of probability with that particular sampling with that particular interval, then you are half done. Now, I would like to say that if we say that a 95 confidence interval for the population mean is obtained by spanning 1.96 times the standard error of the mean on either side of the sample mean. What is the meaning of this? The meaning is this: if we take a large number of samples of size n, say 1000, and obtain the interval estimates from each of these 1000 samples, then 95% of the times these interval estimates would contain the true population mean. And this is basically the result that we wanted to take. In fact, I could take many examples here, but the best thing is that we basically have explained you the sample mean and the proportion, and we also discussed about the population and population variance and how you can estimate the population variance. So basically what is happening is that you are finding the expected value of a sample statistic, and you are finding out the standard error of that particular sampling statistic, and on the basis of that, what you are doing is that you are applying the central limit theorem, and you are converting all your distributions into standard normal distribution, and on the basis of standard normal distribution and the area under the standard normal distribution, what you are trying to do is that you are trying to estimate a confidence interval into which your sample observation would lie. So what you are trying to do is you are trying to generalize that inference that you have derived from the sample, that your population characteristic would certainly lie in a particular confidence interval. And we have explained the meaning of this, that suppose you take 1000 samples and you say that you are 95% sure that your value would lie in that particular confidence interval. So what will happen is that 95% times or 950 times your value would lie in that particular interval. So this property helps you to give a certain kind of inference to the business decision maker, and on the basis of this you can take a decision in future, for the future. Say if you want to ascertain the number of units that a particular manufacturer has to produce, then what you will do is that you would take the upper limit of the interval and the lower limit of the interval, and you can aid the inference. So basically I have given you an overview of quantitative techniques, and I have given you a basis for doing applying quantitative techniques. With this we would like to wind up this session. I am Professor Anurag Saxena, and you can mail to me if you have any doubts regarding this particular course. I'll be very happy to answer you. With this, we'll close this session. Have a good time. Thanks.